Hello and welcome to ML with AP. We have come to the absolute end of ensemble learning. This is the video 2 of XGBoost. As promised, what we are going to do today is to go over the maths behind XGBoost, as well as we'll try to code XGBoost using Scikit-learn. Let's jump right in. Okay, so I tried to make some deck how I used to make. Then I found an internet and I was doing the reading. I wanted to show you actually the deck which is prepared by the founder or the inventor for this particular module, right? So let me just open that. Okay, so this was done in 2015 or 16 by Tenaki Chen, and he is the presenter. I will link this particular slide deck also in the description below in the YouTube channel. But I think when I was trying to prepare the deck, I thought that I cannot do a better job than what the founder of this algorithm has already done, right? So why not? I will just try to walk you through this particular deck and give you the flavor of it, right? Okay. What I also intend to do is to see the XGBoost and how we can code it using the Scikit-learn wrapper. As I have already mentioned in the previous videos, and friends, this is very important. If you have not watched my part 1 of this, or the gradient boosting of this, or the decision tree, it's very important that you watch those, right, to make sense out of this, right? Okay, so these are the two things which I want to do. Before that, this is the original paper. I will also try to link this paper by Tenaki Chen, and this is what he has done and he has published, right? I will try to link this also. This is, you can try to go through at your own pace, but let's see that how XGBoost math works, right? And I will not go into since this is a very complex model, I will not go into the gory details. I will try to give you a flavor of what the math is all about, okay? So let me just, I'll try to, it is built on top of gradient tree boosting, right? That's why he has given the references of this, right? So the random forest, which was by Bremen in 1997 proposed, 1999 gradient tree boosting came, and then in 2015 or 16 something, your gradient tree boosting with regularization, right? So if you notice, the XGBoost is already inbuilt with regularization, right? So that's how it was presented. Now, what he's saying is the advantages of tree-based methods, right? What are the advantages? The tree-based model, not the ensemble, but the normal decision tree, it's very easy to interpret and control, right? Explainability is very high. It is highly accurate also, because you're doing if-else condition. So if you are not completely overfitted the tree, it will have good predictive power also, and it is easy to use. Everybody can learn that. Challenges: if you let it grow to a huge extent or fully grown, then it has a tendency to grow into an overfit situation. Okay, and the training speed is also challenging, right? Especially for the large or big data sets. Okay. Now this I think we have already dealt in some way. This is important, right? So the objective function for your XGBoost is a combination of your laws, your traditional laws of the regression laws, and the omega. Omega is nothing but regularization. So friends, I have already told you that regularization is baked in XGBoost, right? What it means is my loss, in case of regression, if I am taking a mean square loss, will be yi minus yi hat minus yi the whole square, right? Summation. This is my mean square loss, or RSS, right? My objective function is a combination of mean square loss plus my L2 or L2 loss, right? L2 penalty. The L2 penalty is lambda and norm 2, right? The weight square. This is what beta 1 square, beta 2 square, beta 3 square, right? So if you have not watched my video on regularization, probably this is a good time to go and watch that as well. Okay, over here, we can skip these. Okay. Now, these two things work in different directions, right? Your loss, traditional loss, mean square loss, and your regularization. If you are optimizing this, what you are inherently doing is that you are trying to minimize the difference between your prediction and your observation, right? So you are trying to closely mimic your predictions, right? Observation and prediction. That means it has a chance of what it works is that minimize the training loss. So it has a chance of going into a high variance situation, right? What this will do in turn is regularize, that make our model simpler, do not make it complex, right? This is what the regularization techniques are, right? So when you reduce the complexity, it will not let you overfit. This guy is trying to overfit, and this trying to stop it from overfit. This is trying to make the model more simpler and simpler, right? So this is the basically, one is going into the overfitting situation, the other is preventing you from going the overfitting situation, right? Okay. Now as I was saying that, okay, that how the your in case of, if you have watched the first video, in case of how the best split of the tree is, we are not going by entropy or gene impurity, right? What we are doing is the similarity score, right? Now, why similarity score? Why difference, right? The similarity score is computationally simple also, right? If you think about that, in case of entropy, we have to take a natural log. In case of your gene impurity, you have to take the squares of that. But in case of similarity score, you only have to sum them up and square one time. So for a large data set, similarity score is much more computationally simple than gene impurity or entropy, right? Now, we all know that XGBoost is a boosting technique, gradient boosting technique, and it is an additive model, right? What additive model means? The additive model means that okay, over here, my tth iteration, right, yit, is nothing but the last iteration plus a new function. What was this new function? This new function is the output on my pseudo residual, right? So when I fitted the tree of the yt minus 1 or t minus 1 model, then after that, if I multiply it by learning rate eta and then multiply it by whatever was the prediction from my pseudo residual, right? That step size, the step of the gradient, this is what it is. So it is additive in this sense, right? Additive training. Okay. Now this is important over here, right? And there will be a little bit of hand waving from my side, but try to stick with me and try to see the intuition behind it. This particular thing we understand, right? This is my loss. My loss is the yi observed, then the prediction, and then this additive term, the prediction from the last one, and then this additive term, right? So if you recall my spreadsheet example, this particular thing is nothing but yi, right? That y from the last prediction, y I had, and then eta, the learning rate, into the prediction, right, on pseudo residual, right? This is what it is. Correct? Now let's see in my Excel sheet, which I have used in the first video also, how this thing expands, right? yit minus 1 is my prediction from the last iteration, right, or the last tree. ftxi is my prediction of the pseudo residual multiplied with my eta term or the learning rate. This yi is my observation from my true observation, right? Okay. So over here, if you see, this t0 is my yt minus 1, right? My one previous iteration was 17.2, right? What I'm adding it over here, eta into predictions, right? And how I'm getting the prediction? I'm getting the prediction through this output value, right? And eta is my learning rate, a hyperparameter, right? I'm multiplying it by that, I'm getting that eta, and that's how I'm getting the t1 predictions. Similarly, I will bid t1, t2, t3, t4, tn, right? How many iterations we have to, or how many additive models we have to build, right? This is what it is. In case of your, if you're doing a mean square loss, right, or a square loss, what we call, this particular thing, this particular term will result into this. Now this is not magic, right? From this, to jump over here, what you need to know is Taylor series. That's where the hardcore maths comes, right? So what is Taylor series? Taylor series is nothing but a function approximation technique used in maths, right? And if I have to say, then simply explaining, it will be that, okay, if suppose there is a very complex function, and if we have to approximate that with our let's say, polynomials, right? The set of polynomials. Then this is how it will expand up to. What it will say is that, okay, I do not know the true function, but if within this range, if you give me the first differential, second differential, third differential of those functions, right? First differential is what? The tangent. Second differential is the tangent of the tangent, or the differential of the tangent. That means which direction it is curving, right? Which direction it is moving. So in nutshell, with this particular approximation, which is Taylor series approximation, right? What you can do is we calculate what this will be, and when you solve it using Taylor series, right, then what you get it over here is this. Now this term, if you see, this term which you see is nothing but the residual from the previous round, that ftxi and yit minus 1 minus yi, right? This is the pseudo residual into this, right? This is what it is. So in terms of square laws, and this is strictly in terms of mean square laws, right? In case of mean square laws, what will happen is that if you calculate the first gradient, right, or the first differential rather, then the first differential of the mean square laws is 2 yit minus 1. This is just with respect to yit minus 1. This 2 will come in the front, correct? In case, and this is h, this is the second differential, del square. The second differential is also called Hessian. That's why it is represented with h. And the first gradient is gradient, first differential is gradient. In case of mean square laws, and especially in case of mean square laws, it will be 2 right over here, correct? Now little more math over here, okay? And the way to do that is, okay, now my omega, if you rearrange the previous terms, right, through Taylor series approximations, what it results into is my gradient of ftxi half into Hessian ftx square xi plus omega. This term we have still not dealt with. This is what regularization term. My regularization term is nothing but gamma t plus lambda half beta 1 square, beta 2, or weight squares, right? This is what it is. When we rearrange this, it looks like this, right? Over here, if you do further maths over here, what ultimately it will become is, let me show you. Yeah, your objective function, or the thing which you are trying to minimize, is coming nothing but gj square, my gradient square, sum square, and this capital G is nothing but the sum of individual gradients, or small g's. Then Hessian plus lambda plus sigma t, or omega, not omega, gamma t, and t is the number of iterations, right? This is what it boils down to, my objective function. Now, if you notice the objective functions which we were dealing, right, over here, this thing, right? Where is it? Yeah. My sum of residual is nothing but my gradient. My sum of residual is nothing but my gradient, right? That's why my similarity score is coming gradient square by n. In case of mean square laws, my Hessian is nothing but n, or the number of elements in that. So this particular formula actually translates to like how similarity score is coming, why similarity score is coming like this. The mathematical proof behind that is this, right? That you have to take a gradient square plus Hessian plus lambda, right? This is what it is. And this gamma into t, and since we have only dealing with one iteration, I was telling you that it has to cross the threshold. This is what the gamma, the relevance of gamma comes over here, okay? Yeah, probably this is the better form, right? So now you can appreciate that gain was left similarity plus right similarity minus root similarity. Similarity is this particular thing, right? This is what your formula we have done, blindly dealt with earlier. Now, in case of this mathematical explanation, you can see that it is the gradient square by the left child. This is the left child, this is the right child, and this is your root. and this is your threshold which you have to cover, right? This is what I was talking about, the gamma, right? So gradient square by Hessian plus lambda, gradient square right plus Hessian plus lambda. This is more generic expression. In case of mean square loss, this becomes specifically to this. So if suppose you are employing a different loss itself, right, then obviously your gradients and Hessians will be different for that particular loss. Then this is a more generic formula. In case of, let's say, logistic regression, you are doing the log loss. Then you have to calculate the gradient and Hessian like this and deploy this formula for the gain, right? Which is very similarly over here, right? In case of mean square loss, and our example, it is coming like this. Okay. Now we already know that how the best split is done. Then quantile approximate a sketch, and the splitting is strictly done how splitting is done in case of gradient boosting and all, right? But the main takeaway from this is this particular formula, right? That how the gain is calculated and how the gain is related to gradients and the Hessians, right? This is the main takeaway. If one thing we have to take away from this particular video is this particular intuition, right? So that if the loss changes, then still you should be able to calculate your gain and the output values, and you should be able to fit your XGBoost. Okay, so this was the original paper by Tinaki Chen. I tried to explain you. I will link it up over there. Now let's go to the XGBoost Scikit-learn. Okay, so XGBoost is released. Let me show you. This is the original paper. Yeah, this is the XGBoost DMLC. So it is not officially part of Scikit-learn. It is a separate API, separate packages. But to make it combine with Scikit-learn, there is a wrapper which is available, and we'll make use of that wrapper. But let's see, I wanted to show you some of the hyperparameters which we have been talking about, right? So eta, the default is 0.3, and this is nothing but alpha actually, right? If you see, the range is 0 and 1, similarly like alpha, and this is the step size shrinkage. What is step size shrinkage? In case of gradient descent, if you remember how much smaller steps you are taking, that is the step size shrinkage. Okay, now what is this gamma? The gamma range is 0 to infinity, right? And again, it's a hyperparameter achieved through your cross validation and hyperparameter search. Minimum loss reduction required to make a further partition on a leaf node of the tree. That means the gamma is the threshold. If you cross that threshold, right? What we are writing over here, gamma was the threshold, right? Correct. If this thing, if my gamma is 60, I will not do this split. If my gamma is 58, I will do the split because my gamma is still positive. Gain minus gamma, right? If the gain minus gamma is positive, I will do the split. If the gain minus gamma is not positive, I will not do the split. So this is the threshold. Then the other parameters of the tree, max depth, max child, all those things are there. Let me show you the another parameter, which is lambda. Yeah. Lambda is the L2 regularization terms on the weights, right? So similarly, but lambda is used in more terms to calculate the output, to calculate the similarity score also. But it is primarily the L2 regularization penalty. Now, why this eta came and not alpha? Because alpha, if you put a L1 regularization, then that term is called alpha. So that is taken. That's why what Tinaki Chen and other would have thought to call this particular learning rate as eta in case of XGBoost, right? But essentially it's the same gradient descent learning rate, step size, all those things. Okay. Now let's see, this is the other one. Yeah, I think we can go to the our Jupyter notebook. This is our Jupyter notebook, XGBoost, right? What I'm doing over here, I'm importing the data set, train test split, min max scalar, pipelining, XGBoost regressor. I'm not using actually pipeline or scaling, I think. No, I'm using a scaling. Okay, I'll leave it. Then XGBoost regressor, right? So if you notice, I'm not importing it from Scikit-learn, right? So Scikit-learn is not available. XGBoost is not available, but as an independent package, right? XGBoost. So I'm importing XGBoost regressor from XGBoost package. Similarly, from linear Scikit-learn linear model, linear regression, random forest, ADA boost, gradient boost, boosting regressor, right? All those things, and SV regression, support vector regressor also I have imported. What I did is I imported the California housing data set over here. I did a train test split with the default. I didn't change anything. Okay. The intention is to just show you that how XGBoost regression works along with the Scikit-learn wrapper. A scalar is min-max scalar. Okay. I did the fit transform over here. Then I passed it through my linear regression model, and I tried to calculate my basic score, right? What is the linear regression score, right? It came at 60%. Okay, fine, 60%. I did the same thing with SVR, with same thing. It came to 66.34, little bit improved. I did the same thing with random forest, right? Again, through scikit-learn packages, it is just dot fit, right? You have to run dot fit and dot score you have to calculate. So 66.31. And friends, if you notice, I'm not doing any hyperparameter tuning for any of them. I'm just going with the default. I wanted to show you that why XGBoost is so popular, right? And how it is used. These are the two intentions. So linear regression, default parameters. SVR, default parameters. Random forest, default parameters. All are in 60s. XGBoost regression, and this is the wrapper, right? I was talking about. Since you have XGBoost regression, I can do a dot fit. If you notice, I didn't use the XGBoost package how to fit the model and predict the model. I'm using the way I used to do in the scikit-learn itself, right? So I'll do a dot fit over here, and then I did a dot score also on this object, XGB regression. And if you notice, it came immediately 84%. With any hyperparameter, without any hyperparameter tuning, it came 84%. So from 60s, it came directly to 84. Just by using XGBoost regression, you can jump maybe 20-30% in predictive power just for the default. If you tune it further, it will go to 90-95% also, right? So this is how we use XGBoost along with scikit-learn, right? With that being said, I think I will close this video at this point in time, and I hope you like it. If you like, let me know in the comments, and we'll be happy to make more such videos. Thank you. Bye.